Good morning all. Welcome to the next lecture. In the last lecture, we were discussed the different types of functions like into function, onto function, one-to-one function, many-to-one function, identity function, constant function, and finally the function with one independent and more than one independent variables. So now we are continuing lecture here by discussing the remaining types of function. See, one of the most important type of function is explicit and implicit functions. A function is said to be explicit, see, when the relationship between two variables, say for example the dependent variable y, is expressed directly in terms of independent variable. That is the most important criteria of the explicit function. See here, we are directly expressing, that is what actually the dependent variable is and what actually the independent variable is. Then the relation between x and y is actually called, it is an explicit function. Mathematically, we can write the explicit function, see y is equal to function of x. See here, the y is the dependent variable and x is the independent variable. For example here, y is equal to 2x plus 3x square plus 8. See here the relationship between the dependent variable and independent variable is expressed explicitly. That is the most important criteria. So as it come understood from the equation itself, see y is the dependent variable here and x is the independent variable. And y is the function of only one x variable, independent variable x. So here we can say that the relation between dependent variable and independent variable is expressed explicitly as it can be understood from the given equation itself. See, we can easily understand which variable is independent and which variable is dependent here. See here it is y is the dependent and x is the independent variable. Now, on the other hand, we said that a implicit function, see a implicit function is a function when the relationship between the variable, say the dependent variable and independent variable cannot expressed directly, or we can say that it is an equation involving both the dependent and independent variable without explicitly solving for the dependent variable. For example, see, it is x square plus y square is equal to 16. See here, there exists some relationship between x and y, but it is not given explicitly, or we can't explain the relation at first look assuming which variable is dependent and which variable is independent. So here it is not explicitly given which variable is independent and which variable is independent. So this type of function is generally known as it is an implicit function. Now another type of function, see, we can say it is single and many valued function. A function such as that one and only one value of y correspond to each given value of x. It is generally known as single valued function. For each and every value of y, see, we will have a single value for each given value of x. It is the type of function in which each element in the domain correspond to exactly one element in the range. That is, for every input value, there only one output value. So thus single valued function does not have multiple y values for a single value of a x. See, we can explain it by using an example. See, y is equal to 6x plus 3. Here we can assign any value for x. We can assign any value for this independent variable x. We get only one value for y accordingly. Suppose we assume that the value of x is equal to 2. Then it will become 6 into 2, which is equal to 12 plus 3, so which is 15. So we have only one value for the y variable. So this type of function is generally known as it is a single valued function. Now as against the single valued function, we have many valued function as well. See, a function such as that more than one value of y correspond to each given value of x, which is said to define y as a many valued, or it is also known as it is multi-valued function. So here it is a type of function in which each element in the domain may correspond to more than one element in the range for some input value. So there can be each and every input value, there can be a multiple output values. This can be understood by using an example. See, y is equal to plus or minus under root 16 minus x square. Under root 16 minus x square. See, here we will be getting two different value for y when we assign any value for the independent variable x. That means, see, for each value of x, there are two corresponding value of y. One positive value and one is negative value. Therefore, a single input x can give rise to two possible output value in this case, that is y is equal to plus or minus under root 16 minus x square. So therefore, such a single input x can give rise to two possible output values of y. If we are assuming the value of x is 2, then the value of y will be, for example, you are going to substitute the value of x is equal to 2. So the value of y will be plus or minus under root 12. It will be under root 12. So this is a characteristic of a many valued function. For each and every y value, there will be two output values. So this is the many valued function. Now we have a polynomial function. Another type of function is a polynomial function. See, a polynomial is an expression of a finite length which is constructed from, see, variables, or it is determinates and constants using only the operation of addition, subtraction, multiplication and non-negative integer exponents. That is the important criteria. So here it is a mathematical expression which consisting of variables, coefficient values and also non-negative integer exponents. So if you go for writing the polynomial function, we can generally, it is in the form of, it is a0 plus a1x plus a2x square plus a3x cube plus up to anx raised to the power n. This is the general form of a polynomial degree n. This is the polynomial degree n, where a0, a1, a2, a3 up to an are the constant or the coefficient of the variable x, and n is the non-negative integer. It is the non-negative integer representing, the degree of the polynomial. It will represent the degree of the polynomial. So in the definition of a polynomial function, the operation of addition, subtraction and multiplication are allowed, and the exponent of the variable must be non-negative integer. That is the most important criteria, especially for creating a polynomial function. So you should be kept in mind that the division by the variable or negative exponents is not allowed within the standard definition of a polynomial function. So a polynomial function can be a constant, linear, quadratic or cubic based upon the degree of independent variable. It may be different forms. It may be a constant function, it may be a linear function, it may be a quadratic function, it may be a cubic function based upon what is the highest degree of the independent variable. See, let's look what actually the linear function means. See, linear function is the first degree polynomial of polynomial function of one variable. It is the first degree polynomial of the function of one variable. See, these functions are known as linear because they are precisely the function whose graph is straight line, and it's generally in the form of, f of x is equal to, mx plus b, or it is ax plus b, where m is not equal to 0. If m is equal to 0, then this mx term will become 0. So then f of x is equal to b, it will become a constant function. So m is not equal to 0. So here the f of x is the output, or it is the dependent variable, and x is the independent variable, or it is known as, it is also an input, or most probably, or we can express this m is nothing but in economics we can say that it is a slope. It is the slope or a constant that determine the rate of change in the given function. And b is nothing but it is the y-intercept. Y-intercept means that when x is equal to 0, then what is the value of y, which is nothing but if x is equal to 0, then mx will become 0, then f of x is equal to b, which is generally known as it is y-intercept term. So now here the graph of a linear function, if you go for drawing the graph of a linear function, then it is a straight line. It is a straight line, especially in the Cartesian coordinate system. And the slope m, which indicate the steepness of, line, that is the slope of the line of straight line. So here the steepness of the line, and yb is the intercept point, or it is the point where the line intersect y-axis. It will intersect the y-axis. So the discussion regarding how to draw the linear graph will deliver in the upcoming weeks. So anyway, the graph of the linear function is a straight line. And now let's consider an example of a linear function. If you go for drawing the graph of a linear function, it will look like this. See, this is a straight line. It is a straight line. So this is the graph of a linear function. And you can also understand by using a particular function, that is y is equal to 2x minus 1. So here the power of the independent variable x is equal to 1. So we can say that it is a first degree polynomial. It is a linear function. Y is the dependent variable and x is the independent variable. Here the degree of the variable is 1. We have a straight line upward sloping when we go for plotting the graph. Now the another function which is known as quadratic function. A quadratic function is a type of polynomial function with degree 2. Meaning, that highest power of the variable x will be 2. Or it is a non-linear function. It is a non-linear with a second degree polynomial function of one variable, and its equation generally in the form of f of x is equal to ax square plus bx plus c, where a is not equal to 0. That means if a becomes 0, then this entire term will become 0. So the highest power, then what will be remaining? It is 1. This quadratic equation function will become a linear function. So a is not equal to 0. Here f of x is the output or the dependent variable, and x is the independent variable, or we can also say that this is an input. A, b, c are the constant where a is not equal to 0. So the graph of the quadratic function, if you go for drawing the quadratic function, then it will be look parabola, which is U-shaped or maybe inverted U-shaped. It will be look like this. It is U-shaped, or maybe it is just opposite of it is, that is inverted U-shaped curve in the Cartesian coordinate system. And the direction of parabola, whether it is opening upward or opening downward, which is determined by the sign of the coefficient of a. This sign of coefficient a, if greater than 0, if the coefficient a is greater than 0, then parabola is, it is open upward just like this. And if coefficient a is less than 0, then the parabola will be downward. For example, see, 3x square plus 2x plus 2 is equal to 0. See, this is a second degree polynomial because the highest power in the independent variable here, it is x, that is power is equal to 2. So in this case, this is a quadratic function. If you go for drawing the graph of the quadratic function, it will be an upward sloping. It will be upward just like this. Okay, so here the exponent of x is equal to 2. We can say that it is a quadratic function. There are various methods to solve, quadratic function, just like factorization method. We can use the factorization method, we can use the quadratic formula, or we can also use the completing square method, many others. So these methods will be, we will discuss in the upcoming classes. Now there is another function which is known as cubic function. See, a cubic function is a type of polynomial function of degree 3 with one variable. So here the meaning that the highest power of the variable in this given function, that is equal to 3. So if you go for writing the general form of a cubic function, then f of x is equal to ax cube plus bx square plus cx plus d, where a is not equal to 0. If a is equal to 0, then this entire term ax cube will become 0. Then the remaining function, that is bx square plus cx plus d, will become a quadratic function. So here we should assume a is not equal to 0, and here f of x is the output or the dependent variable and x is the independent variable. A, b, c, d are the constant where a is not equal to 0. So for example, see 5x cube plus 3x square plus 2x plus 2, which is equal to 0. So here the independent variable x highest power is equal to 3. So we can say that this is a cubic function. Now the graph of a cubic function, if you go for drawing the graph of a cubic function, then it have various shapes with ups 2 points, ups in the 2 points where curve can be changed the direction. Here also is turning point, here also we have a turning point. As unlike quadratic function which have only one turning point, but in the case of a cubic function we may have upper side direction turning point, and also we have a lower side turning point. So this is the graph of a cubic function. Now we have another type of function which is known as rational function. See, a rational function is expressed as a ratio of two polynomial, and it is obtained by dividing the polynomial. This function is obtained by dividing the one polynomial by another polynomial. So it is generally called as a rational function. See, the term rational function is coming from the term ratio. See, if we have two polynomial function, for example g of x and h of x, these are the two separate polynomial function. So then we can write a rational function, that is f of x is equal to g of x divided by h of x, where g of x and h of x are the polynomial function. For example, see, f of x is equal to x square plus 1 divided by x square minus 2x plus 5, where denominator x square minus 2x plus 5 is not equal to 0. If it is equal to 0, then only the numerator side will be remaining. So here the numerator x square plus 1 is a polynomial of second degree, and the denominator's highest power is also equal to second degree. So if it is in the ratio format, then we can say that it is a rational function. Now we have another type of function which is generally known as monotonic function. See, a function which is always increases or decreases, we can say that it is monotonically increasing or monotonically decreasing. See, there are two types of monotonic function depending upon the either increasing or decreasing. We have monotonically increasing function and monotonically decreasing function. See, what is a monotonically increasing function? When we assign a consecutive positive integer as a value of x, it's showing an increasing trend. Then such a function is known as monotonically increasing function. For example, see, f of x is equal to x plus 1. If you assign any consecutive number of x, then it is continuously increasing. For example, if you are assuming that x is equal to 2, then the f of x is equal to 3. If you assume x is equal to 3, then f of x is equal to 4. So it shows a property that is monotonically increasing function, where as the input x is increasing, then the function value, that is f of x, is also increasing. See, as against the monotonically increasing function, we have monotonically decreasing function as well. See what actually the monotonically decreasing function means? When we assign a consecutive positive integer as a value of x, then the y shows decreasing trend. Then the function is known as monotonically decreasing function. For example, see f of x is equal to 1 by x is an example of a monotonically decreasing function. For example, if you assume the value of x is equal to 1, then f of x is equal to 1. If value of x is equal to 2, then f of x is equal to 1 by 2. If x is equal to 3, then f of x is equal to 1 by 3. So it is continuously decreasing if you are assuming the consecutive positive integer for the x. So here there is no up and down swings, or there is no oscillation, especially in the case of a monotonically function. So the graph of the increasing monotonic function goes from left to right, always moving upward or remain constant. Similarly, the graph of a decreasing monotonically function goes from left to right, always moving a downward direction or remain constant. Now we have another function that is known as exponential function. See, an exponential function f of x is equal to, see we can say that the example, f of x is equal to a into b of raised to the power x, b raised to the power x. Here f of x is equal to output or dependent variable, and x is the input, and it is a constant coefficient. A is the constant coefficient and b is the base of the exponential function. So the base b is a positive constant, differ from 1. See, if b is greater than 1, the function represents an exponential growth, which means as x is increases, the value of f of x is also increases rapidly. And if we are assuming that if the value of b is less than 1 and greater than 0, then the function represents exponential decay, which means as x is increases, the f of x is decreases rapidly. So here the base serves as a starting point for calculating whether it is a growth or whether it is a decline. For example, the f of x is equal to e raised to the power x is a specific case of an exponential function. Here base b, see, is nothing but it is e, and a is a constant coefficient which is implicitly given, which is equal to 1. So this is an example of an exponential function. Now we have a logarithmic function. See, logarithmic function is an inverse of an exponential function. It is generally known as an inverse of exponential function. The general form of a logarithmic function, that is f of x, is equal to log base b of x, that is f of x log b of x. Here f of x is the output or dependent variable and x is the independent variable. B is the base of logarithm, and log b of x, which represent the logarithm of x to the base of b. See, what is the use of logarithmic function in economics especially? See, in economic model, we are often employ the logarithmic transformation of variable in a given model. It is a common practice to use a logarithmic function, especially transform a certain non-linear economic models to a linear model. So that's why the logarithmic function is generally using in economics, because the linear model is often, it is very easier to work with mathematically, and many statistical techniques can also be assumed in the case of a linearity. So this is about the logarithmic function. Now we have a homogeneous function. See, a function is homogeneous if each independent variable is multiplied by a scalar, which is nothing but, it is a positive real constant lambda, for example, then the constant can completely factored out. That is the most important criteria. That is, this constant lambda can completely factored out. Mathematically, we can say that a function z is equal to function of x and y is an homogeneous of degree n for all positive real value of lambda. For example, if you are going for multiplying the each and every independent variable, that is x and y, by using lambda, so lambda x, we can factor out lambda to the raised to the power n. So here the n, this power n determine the degree of homogeneity. If n is equal to 0, then the function is called a homogeneous of degree 0. If n is greater than 0, then it is positively homogeneous. If n is less than 0, then it is generally negatively homogeneous. Now, a homogeneous function play a significant role, especially in economic modeling. Especially utility function, production function especially. For example, we have a production function, that is Q is equal to function of L and K, where L is the labor and K is the capital. Here, if both labor and capital are multiplied by same constant, for example lambda, then the resulting functional value is nothing but the power of the number of times a function value, that is function of labor and capital. For example, it can be easily understood by using an example. See, Q is equal to 4L plus 3K is a homogeneous of degree 1, because if you go for multiply a scalar, that is lambda, with both variables, that is labor and capital, see, it will become 4 into lambda L plus 3 into lambda K, which is equal to, lambda can be completely factored out. So common here, lambda is common here, so we are taking lambda outside, and in bracket we have an original function, that is Q. So here we can say that it is a degree 1, homogeneous of degree 1. It's showing that if you go for doubling the quantity of both labor and capital, it will result in doubling the output. This property, it is usually associated with a constant return to scale in economics. See, especially it is related to the production function, where proportional increase in input leads to a proportional increase in output as well. Consider another function. See, a production function Q is equal to 3L square plus LK plus 2K square. It is a homogeneous of degree 2. We can prove it. See, if you go for multiplying the each and every element of the given production function, so it is 3 into lambda L whole square plus lambda L into lambda K plus 2 into lambda K whole square. So here we can completely, the lambda can be completely factored out. So here if you remove the bracket, it will be lambda square L square. Here lambda and lambda will be multiplied, so it is lambda square. What is remaining? It is L and K plus lambda square, again it is K square. So here lambda square, it is common here, so we are taking into the outside, or it is completely factored out. So it is lambda square into the original function, which is nothing but it is an homogeneous of degree 2, because the power of the lambda is, or degree of the lambda is equal to 2. So it is an homogeneous function with the degree 2. Now we are going to consider the composition of function, another function, that is composition of function. See, actually it involves combining 2 or more function to create a new function. How it is possible? See, if we have 2 function, for example f and g, then the composition process is denote. See, we can say that it is f of g. It is composed with, we can say that f is composed with g, or we can also say that it is f of g. It is generally created by combining 2 or more function, especially to create a new separate function. So the composition of f of g is formed by applying g to the input of f, and the resulting function is written as, see, it is f of gx, which indicates that the output of the g is used as an input of the given function f. See, we have different types of composition of function. See, the first one, we have a forward function. See, forward composition is a standard form of most common standard form, and it is a most common type of composition of a function, and it involves composing 2 function or combining 2 function in such a way that first we apply one function and then apply the other to the result. See the notation especially we are used for here. See it is f of g, f of g. So here where f is the f and g are the two separate functions. Now here for example we have a two function which is given here, that is f of x is equal to 2, which is not written here. Here f of x is equal to 2x, and g of x is equal to x plus 1. f of x is equal to 2x and g of x is equal to x plus 1. Then how it will be? F of g x, which is equal to, within the function f, we are going to substitute the g of x. As I have already told you, the g of x is equal to 2, and here 2x, we are substituting the value of x as a x plus 1. So it will be 2 into x plus 1. We can solve it. It is 2x plus 2. If you multiply 2x, it is 2x plus 2. This is the forward composition. Now as against the forward composition, we have a reverse composition as well. See, in the reverse composition, you take a first function and then substitute in the second function. And the notation which is generally used for the reverse function, it is g of f. In the initial stage we said it is f of g. Here it is g of f, where f and g are the functions. For example, we have a function that is f of x is equal to 2x and g of x is equal to x plus 1. We have a two separate function, f of x is equal to 2x and g of x is equal to x plus 1. Then the reverse composition, that is g of f, is calculated as, see, g of f function of x, both are function of x, which is nothing but in the g of x we are going to substitute the value of f of x. So here it will be look like, see, 2x we are going to substitute in the x plus 1. So instead of x we are substituting 2x. So it will become 2x plus 1. G of f is nothing but it is 2x plus 1. This is the reverse composition. Now we have another one, that is composite of a function with itself. How it is possible? See, a composition of a function with itself, which is generally considered as a special case of a function of composition. See, where a function is composed with itself, which is generally known as a function is composed with itself, which is generally denoted as f of f, representing the function f composed with itself. For example, see, we have a given function f of x is equal to x square, and the composition of f with itself, which is nothing but it is f of f is a function of x. In the given function we are going to substitute the f of x. So it will be, see, x square. Instead of x we are substituting x square. So it will be x square whole square. And if you open this bracket, then it will become x raised to the power 4. So similarly, if we have another function, see, g, and the composition of g with itself is nothing but it will become a g of g. Okay, that's also a composite of a function with itself. Now we can conclude here in this lecture. We have already discussed different types of function, including the composite function. And in the next lecture, we will discuss the concept of inverse of a function, and we will see in the next lecture. Thank you.